Single-Photon Avalanche diodes, or SPADs, are an emerging optical sensor technology with a unique capability of counting individual photons with very high timing resolution. Due to their ability to precisely time tag individual photons, SPADs are gaining popularity in low light and active imaging applications. For example, a SPAD-based LiDAR uses a pulsed light source in synchronization with the SPAD to estimate scene depth. In this work, we propose a different use case for SPADs. Our goal is not to estimate scene depth. Instead, we use SPADs in ambient light with the goal of capturing 2D intensity images of the scene. There are two key differences in our imaging setup. First, we use the SPAD passively, in ambient light only. There is no active light source, no pulsed laser. And second, we use the SPAD in a free running mode driven entirely by ambient photons and no external synchronization clock. We call this imaging modality passive free running SPAD, or PF-SPAD. In this modality, a SPAD pixel collects light for a fixed exposure time similar to a regular camera pixel. Photons incident on the SPAD pixel follow Poisson statistics. The PF-SPAD has some interesting output response and noise characteristics, very different from conventional CMOS and CCD image sensor pixels. Let us take a look at the photon detection timeline. A SPAD can detect individual photons, but after each photon detection event, it goes dead for a fixed period of time, usually a few hundred nanoseconds. During this period, called dead time, the SPAD cannot detect additional photons. After the dead time ends, the SPAD is reset and ready to detect the next incident photon. Although the dead time causes some photons to be missed, it leads to an interesting response curve. The response curve is the average number of photons detected by the SPAD, plotted as a function of the incident photon flux. We will present a simplified picture here. Please refer to the paper for mathematically precise derivations and technical details. At low flux values, the incident photons are spread out in time, and the SPAD detects almost all of them because the dead time windows do not overlap. At slightly higher flux levels, the PF-SPAD misses a few photons, but the response grows approximately linearly. At even higher flux levels, the SPAD starts missing a large fraction of the incident photons, until eventually, at extremely high flux values, the response curve flattens out as the SPAD pixel spends most of the time being dead. Observe that the response curve slowly approaches a saturation limit, but it never saturates. In contrast, conventional CMOS or CCD image sensor pixels suffer from a hard saturation limit, known as the full well capacity. Although dead time causes a PF-SPAD to miss photons, it gives the unique ability to adaptively reject some of the incident photons and provide intensity-dependent gain. The resulting nonlinear response curve does not saturate. It looks like a tone mapping curve used in HDR imaging and provides dynamic range compression for free. A PF-SPAD also has some counterintuitive noise characteristics. We will focus on two of the interesting ones, shot noise and quantization noise. First, let's look at shot noise. For conventional sensors, it is well known that shot noise variance grows linearly with the incident photon flux due to Poisson statistics of photon arrivals. The x-axis is on a log scale, so the plot does not look like a straight line, but it is a linear function. Surprisingly, the variance in photon counts of a PF-SPAD first increases and then decreases with incident flux. This is because at very high incident photon flux levels, the SPAD detects the next photon almost immediately after the previous dead time window ends, making the counts almost deterministic, one detected photon after each dead time window. Now let's look at quantization noise. For conventional sensors, this noise is often negligible because they use high-resolution analog-to-digital converters. However, when the full well capacity is reached, the variance can be thought of as jumping to infinity because the sensor can no longer distinguish between additional incident photons. This is a hard saturation limit. For a PF-SPAD, on the other hand, the output is an integer number of detected photons, which is inherently quantized. The quantization noise can be thought of as approximately uniformly distributed between 0 and 1, which has a small constant value of 1/12 at all flux levels. This is shown by the blue dotted line at the bottom of this plot. The PF-SPAD does not suffer from a hard saturation limit. However, interestingly, at very high incident flux levels, the PF-SPAD's quantization noise exceeds the shot noise and becomes the dominant source of noise. We call this phenomenon soft saturation. The PF-SPAD's estimated photon flux is a nonlinear function of the photon counts. The noise in photon counts gets transformed into errors in estimated flux through this nonlinearity. It turns out that the soft saturation flux level is reached well beyond the hard saturation limit of a conventional sensor. This enables a PF-SPAD to reliably measure extremely high flux values while maintaining high signal-to-noise ratio. This plot shows the theoretical SNR curve for a PF-SPAD pixel overlaid on our experimental estimates. Our theory and experiments show a remarkable 2 orders of magnitude improvement in dynamic range compared to a conventional sensor. We now show some simulated high dynamic range imaging results. Here we show a simulated HDR image of an outdoor scene. A conventional image sensor with a long exposure time captures details in the darker regions of the scene, such as the text in the shadows, but the sky appears saturated. With a shorter exposure time, the conventional sensor captures details in the bright sky, such as the tree branches, but now the text in the shadow appears grainy and underexposed. A simulated PF-SPAD array captures the entire dynamic range in a single shot. This is a simulated HDR image of an indoor scene. A conventional image sensor with a long exposure time captures the textual details in the shadow, but the bulb appears saturated. With a shorter exposure time, the conventional sensor captures the bulb filament, but the darker text appears grainy. A simulated PF-SPAD array successfully captures the entire dynamic range in a single exposure duration. We now show some experimental results using our single-pixel PF-SPAD hardware prototype. Our hardware prototype consists of a single SPAD pixel mounted on 2 microtranslation stages which raster scan the image plane. This allows us to capture 2D intensity images of the scene using a single pixel. Here we show a scene depicting an imaginary car driving out of a dark tunnel. With a conventional sensor, the regions inside the tunnel, such as the speed limit sign, are captured reliably, but the sign outside the tunnel appears saturated. With a shorter exposure time, the sign inside the tunnel is not legible, but the brighter stop sign becomes visible. Our PF-SPAD prototype captures both ends of the dynamic range in a single shot. The dark text is visible simultaneously with the bright text. Here we test an indoor tabletop scene with a bright Edison bulb casting a shadow on an alarm clock. With a conventional sensor, the digits on the alarm clock are visible, but the bulb filament is saturated. With a shorter exposure time, the conventional sensor captures the bulb filament, but the numbers on the clock are too noisy to be visible in the zoomed-in set. Our SPAD prototype captures both the bright filament and the numbers on the clock in a single exposure. This scene has multiple bulbs at different brightness settings and a book in the dark shadow. With a conventional sensor, the text on the spine of the book is visible, but the brightest bulb is saturated. With a shorter exposure time, the conventional sensor captures the bulb filament and the text on the mason jar containing the bulb, but the text on the book is not legible anymore. Our PF-SPAD prototype reliably captures both ends of the photon flux values. The text is clearly visible on the book, and the bulb filament is visible too. SPADs are traditionally used in niche applications that require precise photon timing information or imaging in very low light. Our passive free-running imaging method shows that SPADs can have a wider scope as general-purpose passive imaging sensors at all light levels. This will have broad implications for situations that require capturing scenes with extreme dynamic range in myriad scientific and consumer imaging applications such as astronomy, microscopy, computer vision, robotics, and consumer photography.